Yeah, real quick before we jump into them, the new type of problem was basically we call it an elevator problem. However, it really could apply to any situation vertically where there's like weight down and some force upward. Okay, we're gonna get into vertical tension problems today, which are gonna be really similar to this. But the situation, the four general types of motion you could have in an elevator, if you watched the discussion and notes yesterday. If you're in an elevator and you're accelerating with a positive acceleration, do you feel heavier, lighter, or the same? Heavier, right? If you do feel the same, your regular old weight, which weight equals m times g, right? F sub g equals m times g. That's your real weight, as long as on Earth with a g of 9.8, right? So what situations in an elevator do you feel just normal? Right, Krish? All right, at rest or moving constant, because A is equal to what then? 0. And then finally, if you feel lighter for any given moment in an elevator-like scenario, then that means acceleration is what kind of value? Negative, right. And one other quick thing, and I did bring this up in the video, but just to point it out again, it really goes back to some real old stuff about acceleration. Just because you're moving upward, does that mean you're accelerating upward? No. Remember, we have to think about what are you doing, speeding up or slowing down, and what direction you're moving in. So I could be moving upward, but if I'm moving upward in an elevator and slowing down, my acceleration is actually which way? Negative, right? In a similar fashion, I could be moving downward and slowing down, and if that's the case, my acceleration is upward. So don't forget all that old stuff. Just because a problem says moving up or moving down, that doesn't guarantee that's your acceleration. Read into it, think. That might be it if it's the right scenario, but it might not be. All right, so that quickly sums up like the new stuff from yesterday. So number 19 was not an elevator problem. It was just a problem using the weight mass equation. All right, so really the only two new equations we have are Newton's second law in general and building the F net side for whatever appropriate forces are there, F net equals ma, and the weight mass equation. Weight, or F sub g, force due to gravity, equals mass times little g. And that's the only one we needed here in this one. It says, on Earth, a scale shows that you weigh 585 newtons. And it obviously uses a term you weigh this, so that has to be your weight. But even if it didn't say weight, if it just said on Earth, a scale shows your 585 newtons without using the term weight, you should still know that's a weight because of what? And not a mass. Weight and all forces are always in what unit? Nope. Weight and all forces are always in what unit? Newtons, right? Weight is just a specific force due to gravity. So if that's provided in newtons, even if they don't say the word weight, you should know that that's its weight. Okay? If it says this is how a scale shows how heavy it is. In part A, it wants to know mass, right? So the formula is Fg equals mg. And another quick review of weight versus mass. Mass, yes, it's in kilograms, or needs to be if we're plugging it into anything. But if we send you to the moon, is your mass still the same as it is here on Earth? Yes or no? Yes. Mass is how much matter you're made up of, how much stuff you're made up of. Whether you're here on the moon or anywhere else in the universe, aren't you made of the same amount of stuff, right? That doesn't change. But weight, because it's also known as the force due to gravity, it is affected by gravity. So if we take you and put you somewhere else where the gravitational field, little g, is smaller, then you won't weigh as much. And that's kind of the point of this question. All right, so we just got to make sure we all realize that mass anywhere in the universe is the same. But weight will vary depending on what g you're in. So the first part was just using this formula to solve for m, and that will be the weight over little g on Earth. And that's going to be 585 divided by 9.8. And remember we said the other day, when solely using the weight mass equation, we typically just use the magnitude of little g, 9.8. And that comes out to be about 59.7. What's the units on that again? Kilograms. But what we got to realize now is that now that mass is good anywhere in the universe, whatever it came out to be, 59.7, right? So in part B, it says, what would the scale read on the moon where g is only 1.6 meters per second squared? Well, on the moon, so we could just subscript this FG sub m for on the moon. The weight on the moon is going to be equal still to m times little g, but it's the new little g, the 1.6, right? On the moon. But the mass is still, like we just said, good everywhere. You're made up of the same amount of stuff anywhere. Take that times the 1.6, so this thing only weighs about 95.5 newtons on the moon. As opposed to, that was the weight on Earth that was given up there, that's the weight on the moon. That mass right here in the middle is the same mass everywhere. We okay on that one? Alright, next one is a pretty typical elevator style problem, very similar to the example. Oh, you have a question still on 19? No. Look to the original given. On Earth, a scale shows that you weigh 585 newtons. That scale is reading weight in newtons, right? So we would assume with a similar scale placed on the moon, reading in newtons would have to get that, right? Does that make sense? There are scales that read mass, and if it was like specific and said what did a scale that reads mass read on the moon, it would still be, what was it, 59.7 kilograms, but not if it's reading weight. Okay. So you actually need, you don't want to get too far into this, but you'd need a special scale on the moon. Even though there are scales, and we use them all the time, on Earth that measure in kilograms, a scale still is, a mass scale like that still relies on gravity pushing the object down into it. So like a mass scale, like we'll eventually use in here for massing things on some labs in the future, would have to be recalibrated if you were going to use it on the moon, basically, because of a different G. But there's actually things called inertia scales, which aren't a typical scale like you think, like getting on it and just reading a number. An inertia scale, you measure the motion that you put in like on the scale, and because of mass and inertia, as we said with Newton's first law, are like the same thing. The rate of motion determines how much mass it is. But that's just a little extra FYI there. All right, so anyways, back to 20. The elevator problem. Use the results from example 2, the one from yesterday, to answer the questions about a scale on an elevator on Earth. What force would be exerted by the scale on a person in the following situation? So some of these we may not have to completely solve for based on what we did yesterday, but some of them we might have to. It depends. So there's 4 parts. I said don't worry about part E, just A through D. All right, so if we're referring back to problem 2, we still have a person in an elevator whose free body diagram would be their weight down. And on a typical bathroom scale, we said yesterday that since the scale is a surface pushing back on you, the force of the scale in this circumstance would actually be what force? When a surface pushes back, we could call it what kind of force? Normal force. But that's what a typical bathroom scale reads, is the normal force on you. In the right situation, it will equal the weight, right? In equilibrium. This person, referring back to that problem, is still the 75 kilogram mass person. And other than that, some new questions. if the elevator moves at constant speed, so remember, I'll still set this all from scratch just to stress it. F net, no matter what's going on, F net on the y-axis for this person on this scale is the normal force minus what? Right, force due to gravity. And that equals m times a on the y-axis. Now, this one says at constant speed, a equals 0, right? That's 0, therefore the whole right side of that is 0, and that again proves how Newton's second law tells us at equilibrium those two are equal. Therefore, the normal force equals the weight, and the weight equals m times g, right? Which is just 75 times 9.8, 735, I believe. Oops. Yeah, 735 newtons. That's because it's an equilibrium. That would read that at rest as well, right? Constant speed or at rest, both a equals 0. Moving along, part B. It slows. Here's where this is what I was talking about to be careful on. The way it's moving alone doesn't make it positive or negative acceleration. So we got to make sure we think here. If we're moving upward, part B is telling us moving upward and slowing down. It says A is 2, but if I'm moving up and slowing down, what do you got to make that acceleration? Negative. All right? So we have to solve the problem with AY equals that. So I go back to the same formula we built above. Just a different acceleration, a non-zero one now. Still got those in here, and that still equals this times that acceleration. Solve for the scale force. In this case, same as the normal force because the scale's pushing back on you. Add the weight over. We found from above that the weight's 735, so I've got to reuse that, right? So we could just say 75 times negative 2 plus 735. And we could see that this term is going to be negative, which will actually subtract off the 735. So we had negative 150 plus 735, and that comes out to be 585 newtons. Again, we should, from concept, be able to predict that. If we have a negative acceleration, and we know our stuff from yesterday, we should predict that we get a smaller answer out than what our regular weight is that we found in part A, right? All right, part C. It speeds up at 2 meters per second squared while moving downward. I'm moving down and speeding up. What's the sign on my acceleration? Or somebody else? If I'm moving down and speeding up, what's my acceleration? Positive or negative? Yes. Careful. I'm moving this way and speeding up. Down, down. If you remember way back to like exercises we did that with learning acceleration. If I'm moving this way, that means I have to be accelerating this way to speed up. The way we described it way back when was the direction of whatever velocity I'm moving at, down, right? And the direction of the A have to be in the same direction to speed up. If they're on opposite directions, that means slowing down, right? So moving down and speeding up, A's got to be negative in that one. So actually, as long as we get that right, I don't have to redo this whole thing, do I? Didn't I just solve it, the same situation for a negative 2? So I just have to realize that, and since I already solved for negative 2 above, we could say, guess what? In this situation, this person's also going to feel 585, right? Because there's multiple ways to feel negative acceleration. Back in the original example, we solved for the positive 2, right? Where they felt heavier. And in part D, another part we actually don't need to do anything for because we already confirmed it. It says in part D, it moves downward at constant speed. Does it matter what direction you're moving if you're at constant speed? No, regardless, whether I'm going up in the elevator at constant speed or down in the elevator at constant speed, my acceleration is still what, guys? 0. If my acceleration is 0, I already solved for that, right? Back in part A, the normal force reading was also equal to the just normal at rest weight because at any constant speed, because that's a form of equilibrium. So we could just restate our answer of 735 that we got in part A. That all makes sense to everybody? All right, the final one was really just another tug-of-war type problem, but I had to assign this one because it involved a cat. Now, when you first read it, it says Marcos is playing tug-of-war with his cat. And the first time I read it, I thought it meant tug-of-war on his cat. That would be more fun. But either way, using him and the cat are using a stuffed toy. At one instance during the game, Marcos pulls the toy with a force of 22 newtons. The cat pulls in the opposite direction with a force of 19.5 newtons. Just like all the other tug-of-wars, this is like the third one now, including an example we had the other day. If it doesn't tell you what direction they're pulling in, set it up whatever way you want, right? Just be consistent. So here's the object we're pulling on, the toy they're pulling on. I'll make Marcos go to the right. So I'm just going to call that force, which is given as 22 newtons, S sub m for the force Marcos is pulling on with 22 newtons. The cat is pulling the other way with a slightly smaller force. I'll just call it FC of 19.5 newtons. And don't forget, although not relevant to the problem of solving it itself, there would still be a weight of the thing they're pulling on, and they're still both combining with some upward force to hold that up and balance on that axis. But what really matters is the x-axis here. The toy experiences an acceleration of 6.25 meters per second squared. What's the mass of the toy? Remember, we got to be careful about direction of acceleration. Well, in this problem, we know both of the poles, right? Those are both givens. This is where you got to use a little common sense. Which direction is this toy going to accelerate? This way or that way? Right or left? Yeah. To the right. You're right. Why? Right. That guy's pulling harder than that cat, right? And that means that if I pointed it to the right, and like normal, we assume the right's positive and the left's negative, then the acceleration would also go at a positive 6.25, right? However, if you happen to put Marcos to the left and the cat to the right, then we would put this as what kind of number? Negative. All right? Either way would be okay as long as you're consistent with your directions. And this time, the mass is the missing thing. But like most typical problems involving like a tug-of-war situation, it's the rightward force, in this case Marcos, minus the leftward force, the cat, equal to m times that horizontal acceleration on the x-axis. Solving for m, all we got to do is divide over a and plug in our numbers. 22 minus 19.5 divided by 6.25. Run these numbers, and the mass of this toy should come out to be about 0.4 kilograms since it's mass. Any questions on that one? After we go over this one more new scenario here in a second. It's not crazy new, it's still similar to a lot of these ones. The plan is tomorrow, after we go over the short homework assignment tonight, I'm going to give you a bunch of problems. The rest of tomorrow, after you watch the video at home of me going over the new ones, you could use the rest of the time to start these new posted problems that are going to be called Chapter 4 review problems. Friday, it's a remote day for everybody. I want you to continue those. Monday, you guys are here Monday, right? Okay, so Monday you'll come in with all those attempted. And I will also, sometime during the day Friday, I will post the solutions of all the review ones. Okay, not as a video, just on a paper. All right, all worked out. When you guys come on Monday, come with questions. Which ones, after looking at the solutions, you don't understand, and then we'll take care of all that Monday, and you can do the at-home test on Tuesday, the open note one. That's the plan for the next couple of days at least.